And what we're going to do now is take a look at the notes for section 2.1. This is the very beginning of the chapter 2 course pack notes, and I'm going to share my screen. Specifically, I'm going to share the visualizer, my little document camera here, so that you can see what's going on. It sort of looks clear. Let me go ahead and hit the focus. Got to force it to be focused. There we go. That's a little bit better. And so what we're going to do in chapter 2 is, instead of looking at individual differential equations, we're actually going to connect multiple differential equations that are all part of the same system. So just like when you're in an algebra class, you learned how to solve one equation, and then somebody came along and said, well, what if these two equations were necessary? Can you solve a system of equations? Well, it turns out you can do the same thing with differential equations. So we've got an example, and this is going to be kind of our example that we'll use throughout chapter 2. And this is a predator-prey model, and specifically the predator in this is the fox, and the prey is the rabbit. And if you've read some of the section on the predator-prey model from chapter 1, you know the background on this. It's just rabbits and foxes, everyday kind of woodland creatures. Turns out foxes, as a general rule, don't prefer to eat rabbits, although they won't shy away from eating rabbits. They don't go hunting rabbits, right? Foxes are not that kind of a predator. But for purposes of our model, we're going to stick with it. So the first question says, well, what are the variables involved in this situation, and what do they actually mean? So the first thing you can do when you're faced with a differential equation is take a look at the derivative part of it, and that'll tell you something. And in both of these equations, you probably have noticed there's a t in the denominator of that derivative, and that tells us that t must be the independent variable. And specifically, it's the time variable. It stands for time. And it's the independent variable for both equations. And one of the key features of a system of differential equations is they're linked together by their variables, just like with a system of algebraic equations that you might be used to from a pre-calculus environment. You can solve a system because they share the same variables. And so this t is the same thing in both. But that's not the only variable that we see. We also see there's an r up top on that derivative, but there's an r here, and there's one even down here. So the r appears in both equations as well, and that's going to stand for one of our dependent variables. And that's going to stand for the rabbit population. And it is a function of time. It is r of t, right? Just like we've seen in chapter 1, the dependent variables are actually functions of other variables, right? But we abbreviate them. We just call it r, even though it's technically r of t. And it appears in both equations. And then there's also the fox variable. F appears in both equations. And no big surprise, that's another dependent variable. And it stands for the fox population. And it's actually f of t, capital F of t, right? And so a couple of things that you probably noticed in looking at this is that in both dr dt and df dt, the units for each term must be, and we take our cue from the left-hand side, must be individuals, maybe predator, maybe prey, but individuals per time. That means each one of the terms in each one of these equations, that means the 2 times r must have units of individuals per time. So that tells us something about the units on the 2 factor there. And so the 1.2 times R times F, that means the 1.2 has to have specific units, right? And so we can use our unit analysis to make sure what's going on. Individuals per time, or you can think of it as population over time, right? As it's same thing. Now, we're not going to get into the weeds on population of rabbits versus population of foxes. We're just going to vaguely refer to it as individuals or population units per time. And of course, I say individuals, but realistically, we could be talking about a situation where the R and the F variable represent millions of, or thousands of, or tens of, right? So I don't know if they're individuals, it's whatever the individual units are for the fox population and the rabbit population. And so the other thing that you probably have noticed about these two equations is that both of the equations have what appears to be a positive term and what appears to be a negative term. So both have growth and decay terms. And you can see that going on. I'm going to use my little highlighter here to kind of make that show up a little bit easier for us. The growth terms are the ones that are natively positive, like that guy right there, and then this guy right here. And notice I say natively positive because R and F are presumed to be only positive, right? Because we can't really talk about negative population of foxes or negative population of rabbits. So that really wouldn't make sense for us to do that. Let me see if I can find another color that won't show up. Oh, I used to have so many wonderful.
Could you move your mouse? It's kind of like on the screen.
Oh, sorry, I forgot.
Thanks.
No problem, thank you. So the decay term is the other guy. It's the one that's natively negative in both equations. Now you'll notice that the decay term looks different in both of them, just like the growth term looks different. In this case, the growth term is just dependent on the rabbit population. So that tells us that in the absence of foxes, the rabbits are going to grow. Just like down here, the individual term, the fox term, is negative, and that tells us in the absence of rabbits, the fox population is going to drop. So we can see something going on in each one of these terms, and we can kind of pull apart what we're seeing. And that's what we're going to do down below here. So let me kind of scoot this piece of paper up. So what are the equilibrium solutions in this situation? Equilibrium solutions, remember, that's where the derivative equals 0. And so the first case is kind of the most obvious case, which is if there's no predator and there's no prey, then there's nothing happening. So no predator, no prey means df dt is going to equal 0, and no prey means dr dt is going to equal 0. Because if you got no prey and no predator, both of these things wind up equaling 0. And this is because since R and F both equal 0. Right? And so if you look at your equations that we're dealing with, the two differential equations are dependent on both R and F. And if both of these things are 0, then it just both of the derivatives equal 0, and it's really that simple. This is sometimes referred to as the trivial equilibrium. It's basically, if there's nothing there, there's going to be no growth, there's going to be no change. But the second case of equilibrium is a little bit more interesting. Right? And we can't presume that R and F are both 0. So in this case, we're going to take our differential equations and kind of tease out what could possibly be going on. So if you imagine a dr dt and you set that equal to 0, you're essentially saying that, and I'm getting this from the top of the page, 2 times R minus 1.2 times R times F is equal to 0. And a little bit of algebra, doesn't take much to see they have a common factor of R. And so 0 equals R times 2 minus 1.2 F. And this can equal 0 two ways, one of which is the rabbits equal 0, right? So that's not very interesting to us. The growth in the rabbit population is 0 because there's no rabbits to begin with. The other one is a little bit more interesting, and it's dependent upon the fox population. It's possible for the growth rate of the rabbit population to be 0 because of the specific value of the fox population. So if you do a little bit of math, you solve this thing for f, you find out that f is actually equal to 5/3. It's basically 2 divided by 1.2, right? And so this is a special case. This is not saying r equals 0 and f equals 5/3. This is saying r equals 0 or f equals 5/3. There's two ways you could get a 0 growth rate of the rabbit population. Now, that's the rabbit population, so let's take a look at the fox population and say, what about dfdt? Well, that can equal 0 if negative f plus 0.9 rf equals 0. That's the other equation. And of course, you can probably spot it. We're going to factor out an f. This is factor out an f, and you have negative 1 plus 0.9 times r, which happens two ways. One of them is not very interesting. That's f equals 0. So if there's no foxes, the fox population doesn't grow. Big surprise. The other one is what happens if the rabbit population is just right. And the just right in this case is the rabbit population is equal to 10/9. Right? And again, I'm not doing decimal equivalents. I'm giving you the exact answer. That is the exact value. And so it turns out these first two are the trivial, right? These are the trivial solution that we saw up above. So I'm just going to kind of circle these and say those are what we got in our trivial situation, right? But these other two are more interesting. The other two are telling us something that if the fox population just happens to be 5/3, whatever that is, and if the rabbit population happens to be 10/9, then both our rabbit and our fox populations don't grow at all. So what we might say in that case is the two populations, the two organisms are in some state of equilibrium, right? They're not growing, they're not decaying, they're not changing. So the big twist for this section, the big twist for this chapter is we are now going to think about our rabbit population and our fox population as two variables that we can stack onto a plane. And so rather than our plane being time as one axis and then a variable in the other direction, we're going to imagine a plane that looks like this. That is rabbit population in one direction and fox population in the other. Now notice, there's no room for time. There's no axis for time here. This is just rabbit population and fox population. So imagine what the r of 0 and f equals 0. Imagine what that point looks like. That would be this point right there. That's the origin, right? And so that's our 0 point right there. But there's another point where we expect there to be equilibrium, and that other point is located when r is 10/9, so somewhere over here, and the fox population is 5/3, so somewhere up there. So 10/9 is just shy of 1. So call this 10/9, and 5/3 is more than 1, so that's a little ways up. And so something like up here at this location of 10/9 and 5/3. Those two locations, we expect to see equilibrium. Now, these are locations on some sort of an RF plane. The two variables, the two population values. This plane doesn't represent anything in reality, right? Movement on this plane doesn't mean anything in time because that's not, neither one of those is a time variable. So this plane represents the relationship between the rabbit and the fox population. So this plane is what we're going to refer to as the RF plane. we're going to call it the phase plane. Now, if you remember from chapter 1, we had the thing that we called the phase line. We had one differential equation that if it was autonomous, it collapsed down to a phase line. We have two differential equations that collapse down to a phase plane. And we'll talk more about what that means. What does it mean to collapse down to a plane in a little bit? But for right now, when I say phase plane, I'm talking about the two dependent variables stacked on a plane on the two axes. Right?
So where on this plane would like the foxes be beating the rabbits or something?
That's the question. So all we've done is identified the two places where there's no change. Like if you started at that point on the plane and then I turned on the time and let the time roll forward, you would stay at that point forever. And if you were at this point right here, you would stay at that point forever. Anywhere else, would it move? If I were a point like here, what direction would it move? Would it move quickly? Would it move slowly? I don't know. All we know is where equilibrium happens. So I'm going to flip the page and we're going to go take a look at the next thing. Now that we've introduced the phase plane, we're going to take a look at a couple of other cases. And we're going to try to tease this out and find out what happens in the on the phase plane. So we're going to suppose that there are just no prey. So that means no prey means rabbits equal 0. And so that means all the initial conditions that we're going to be talking about, any initial condition is along the F axis on the phase plane, right? Something like this. It would be 0, comma, some initial fox population. A little f with subscript 0, meaning at time 0, you have some initial value, some initial amount of foxes, but there's no rabbits. Right? So I'm just going to remind us this means rabbit initial equals 0. So what do our equations predict? Well, we have two equations, remember, and this is a system, so we have to think of both of them. The first equation is what's going on with our rabbit population. Now, you guys know what's going on with the rabbit population because that's just 2 times r minus 1.2 times r times f. And since r appears in both of these terms, if we plug in 0 for r, you know what happens. This is just 0. So nothing is changing in terms of the rabbit population. So dr dt equals 0 for any initial condition, that is the equivalent of 0, comma, some initial fox population. That's just goes without saying. So our dr dt was easy. The other one is a little bit more interesting because the other equation is in terms of talking about foxes. So df dt, the equation for that, if you remember, is equal to negative f plus 0.9 rf. And of course, rabbit population is 0. That was our stipulation at the beginning. So that means this whole term is equal to 0, but not the whole equation. So it turns out our rate of change of the fox population is equal to negative f. And so whatever you plug in as your initial population for the fox population, that determines how quickly the fox population will decay, right? There's a decline in the fox population. So if you have an initial fox population of 1 unit, then initially it's going to decay at a rate of 1 unit per time. If you have an initial fox population of 2 units, then it's going to decay faster. This is exponential decay, as we've seen it before. And I saw a question pop up. I just got to grab the mouse and do this. So I saw somebody posted something in the chat. Let me just make sure here. Boop. So just call me Austin having computer issues. Oh, sorry. Emma's having computer issues. Sorry, I got to pause and get a drink anyway. So, okay. So we expect exponential decay for the fox population, but we don't expect anything in terms of the rabbit population because we started with none. So that means if we were to, and off to the side, this is what I'm going to do. I'm going to draw a picture on our RF plane. Rabbits go this way, foxes go that way. And so if you imagine the only quadrant of this graph that makes any sense is quadrant 1. Since, of course, the rabbit population and the fox population are both greater than or equal to 0, right? So just as a general rule, we don't really care about anything going on outside of quadrant 1 for our phase plane here. But what would an initial condition like this look like? Well, it would be anywhere along the f-axis, but nowhere outside of the f-axis. So let's imagine 3 distinct initial populations. And so that point is 0, 1. That means an initial population of 1. And then maybe another one up here at 0, 2. So that means we're talking about another initial population of 2. And last but not least, we'll have a third population up here at 0, 3. Okay, these are just examples for an initial population. And so in each one of these cases, what this equation's telling me, well, these two equations are telling me, is that there's no change in the horizontal, right? I don't suddenly move horizontally because this is telling me that there's no change in my horizontal position. But my vertical position does drop. It drops at a rate proportional to whatever the population size is. So in this first case, where f of 0 equals 1, that means df dt starts off at -1, which means it's going to be a downward motion at about 1 unit of fox population per time. Let me scoot that up a little bit. And likewise, if I do the same thing here, that means df dt is going to start off at -2. Now negative because it's going down, but now it's going twice as fast. You can think of it as traveling twice as far along the axis. And for those of you playing the at-home game, which is all of you right now, you probably are starting to think, hey, arrows twice as long, pointing in the same direction, this is starting to feel a lot like vectors. And that's exactly where we're headed. And for our third example here, df dt is -3. If you start with a bigger population, you have an even larger downward trend for your population in terms of the decay. So what we see is, even though in all 3 cases, they're going to be headed downward along the axis, the one that is further away from the origin is going to be moving quicker in time, right? If you imagine time affecting us here. So these are all situations where no rabbits exist and the fox populations are essentially going to die out over time. So all examples where there's no rabbits and the fox population is dying off. Right? All 3 examples. They're headed for the origin, which is a bad place for a population to be, right? 0, 0. So this is telling me not just the rate of change of the rabbit population, but on the phase plane, it's telling me how quickly my solution curve moves in the horizontal direction. So this piece of information is how quickly a solution curve moves horizontally. And this one right here, that's telling me how quickly a solution curve moves vertically. Because, of course, the fox population is in the vertical direction on our phase plane. And if you put them together, you have how quickly does it move this way and how quickly does it move this way, which describes on a plane how quickly it moves in any direction that you might want to go. You just break down your motion to horizontal and vertical motion. So my phase plane, you can think of it as parameterizing, right? Turning it into parameters, the equation in terms of time. They're both parameterized with respect to time. So what happens down on the bottom of the page? What happens eventually to the predator population? If you wait long enough, what's going to happen to our predator population?
They all die.
Bye-bye. No more foxes. They dead. Wah, wah. Right? And so this really is a limit argument. We would say that as, to be a little bit more mathematical, as t approaches infinity, the fox population, f of t, heads to 0. R of t is already there. There's no rabbits to begin with, which means that you're going to expect in the long run the fox population will die out. And remember, this is anywhere that the rabbit population is equal to 0, which is along that f-axis. So guess what we're going to take a look at next? Since we've looked at this axis, we're going to take a look in the other direction, take a look at the other axis. And we'll do this relatively quickly because I think you're getting the idea. So on this next page, we're going to suppose, for starters, that there's no predators. And that means, no predators means f equals 0. Our initial fox population is equal to 0, and that means it doesn't change. Fox population stays at 0 forever and ever and ever. Amen. So it's only rabbits. And if there's one thing you know about rabbits, they're cute, but they think each other are cute as well. Rabbits love to love, and rabbits will reproduce like crazy. So on the RF plane, this means the initial condition would be equal to some initial rabbit population, comma, 0, because that 0 is the fox population initial is equal to 0. So what do our equations tell us? Well, dr dt is going to be a little bit more interesting this time. That's equal to 2 times r minus 1.2 times r times f. And since we know the initial fox population is 0, this whole term goes to 0. And so my rabbit population is just has an equation, a differential equation that looks like that. We've seen this before. What does this mean for the rabbit population? What do we expect r of t to look like if that's dr dt?
Exponential growth.
Hey, all right. That's exponential growth. As a matter of fact, we could actually even say what the solution equation is for r of t. It's some constant times e to the 2t. That's what r of t looks like because it's no longer dependent upon the fox population because it's 0. So that's dr dt. And of course, we also have to consider df dt. And of course, as the setup would indicate this is just going to wind up being 0 because it's negative f plus 0.9 rf. And since the fox population of 0 is in each one of these terms, the whole thing is just equal to 0. Right? So it's not interesting in the f direction vertically, but it is interesting in the horizontal direction. And so if we draw our rabbit and fox population like this, draw our f axes, then no matter where you start along the rabbit population, whether you start at some R1 here or some R2 or some R3, if I can find another color here, no matter where you start, you're going to expect there to be growth in the rabbit population. But remember, growth on this graph doesn't necessarily mean up. And it doesn't mean, at a particular angle. It means growth in the rabbit population alone with no change in the fox population. So that means it can only go to the right. So you would expect this kind of growth. And of course, because R2 is a larger R value, bigger R means bigger growth, which means it's going to have a longer arrow. And R3 is going to have even longer arrow. Longer arrows because bigger population. The growth is larger because it's proportional. The growth rate is proportional to the population size. Right? So the punchline for this is the larger the rabbit population, to begin with, the faster it grows. That's kind of the textbook definition of exponential growth, right? The larger it is, the faster it grows. But notice it's only along the R-axis because the fox population ain't going to change. There's no foxes to begin with. So now what? Well, what about any other point? As Stephen asked earlier, what about any other point on the graph? What about when the rabbit population is 1 and the fox population is 1? Right about that point right there. What about if the rabbit population is 15 and the fox population is 12? And the answer is, well, we could throw in some numbers and find out what the derivatives are doing. But it's not going to draw the curve for us. It's just going to tell us what direction the curves are going to go at that moment. So down at the bottom it says, what happens eventually to the prey population? Well, it's growth without bound. And without bound just means as t approaches infinity, the population approaches infinity. So a little bit more mathy. As t approaches infinity, r of t also would approach infinity, which of course is not realistic at all, at all. But what we're going to do now is try using Maple to answer the question of, yeah, what about anywhere else? We've seen what happens along the two axes. We know there's an equilibrium point floating out there in the plane and one at the origin, but what about everywhere else? How do we visualize this? And so that's what we're going to try to do next. Let me close my markers down. And now we're going to try to switch over to, if we can figure out how to do it, switch over to Maple here. So on Maple, and I'll make this available for you guys to be able to get access to anytime you want. The problem is I think my computer is giving me fits. Oops, let me go up here. My computer is giving me fits, and so I have to be really careful about doing too much too fast in Maple. So I'm going to show you some kind of pre-generated stuff. If you want to type stuff in, that's fine. You want to throw stuff in Maple and try it out on yours, that's fine. But we're going to kind of talk through what we're doing. So you'll notice I've defined my rabbit and my fox population equations. So this is dr dt, this is df dt. And I've named them rab and fox just for reference purposes. And so both of them are rates of change with respect to time. And inside the equations, I have to refer anywhere to R as R of t and F as F of t. That's how Maple knows these are actually functions and not just unnamed constants or undefined constants. And so it turns out you can just do a D-solve. And this is what you get. You look at it and you go, oh, F of t equals 0, R of t equals constant times e to the 2t. Hey, that looks familiar. Yep, that's one solution. One possible solution is there's no foxes and the rabbit population takes off and grows to forever. The other possibility is everything inside those brackets. And as you can probably tell, this is above our pay grade. This involves not only a root of and an integral, but somebody's name. And whenever you see somebody's name in an output in Maple, that means that it's fairly complicated. And actually, that is hiding a different integral function there, the Lambert function. And so making sense of this is not going to be so easy for us to do as a direct analytic solution. But what we can do instead is do a DE plot. Now I want you to take a look at, here before we take a look at the actual DE plot, I want you to take a look at the code. And I'm going to bump up the size of the font here just so that you can see it a little bit better. Take a look at the code, the way I've typed in the DE plot. I've identified the equations, because it's a system, in brackets. So we've got the rabbit, comma, fox. So I've got my two equations, and then right after that, I have my two variables, R of t and F of t. And it does matter that you're calling the variables the same thing that are in the equations. If they're not the same thing in the equations, then all hell breaks loose. And then right after that, I start with my independent variable, which of course is time. And so I'm going to use 0 to 10. That'll be my time frame for this. And then after that, a whole series of initial conditions. Now take a look at those initial conditions. What do you make of those? How do you read that first initial condition?
I'm guessing it's the t value, the rabbit value, and the fox value.
Beautiful. The first number in that ordered triplet, not ordered pair, but an ordered triplet, is the value for time. The second, because you've identified the second one to be the rabbit, and then the third one to be the fox population. So that means 0 time, 2 rabbits, 2 foxes. Then the next one is 0 time, 1 rabbit, 1 fox. The next one is 0 time, 3 rabbits, 3 foxes. And then the last one is 0 time, 4 rabbits, 3 foxes. And then just like we would have done with a DE plot before, we had to say what's our dependent variable range. But this time, of course, we have 2 dependent variables. And so we get R and F defined over a fixed domain, 0 to 5. I just did 0 to 5, mostly because that seemed to fit these initial conditions. And then, of course, I made the line color be different for each one of them so that we can actually see which one is associated with 0, 2, 2, and so on. And so taking a look at the graph, the output for my, let's see if I can pull this thing up. Boop, boop, boop. Stretch this thing out a little bit. You can see there's the red and the blue are really, really close to each other. Then there's the green, and then there's the, I assume that's turquoise out there. And so you can identify each one of them. And it turns out red and blue, these first 2 initial conditions, are actually very similar curves on the phase plane. So here's the question. What would change about this graph if I change this 10 and instead made it 1? How would that change what gets produced on Maple? What do you think? If I change it to a 1, and I'm going to risk it, I'm going to go up to the top and rerun my DE tools. Oh God, this is so slow. My computer is being really flaky today. I don't know why, but if I scroll back down, now that I've run DE tools again, and I change this thing to a 1, what did you predict will look differently about my DE plot? Is it going to change those red arrows? Is it going to change the directions? What do you think? Let's find out. I don't know if this is going to work because my computer's being flaky, but we'll give it a try. Oh, check initial. The number option must be specified before initial conditions. Oh, what did I do? What did I do? No, that's right. What's wrong with my code? Oh, probably because it doesn't recognize my equations here. Hold on. Rabbit, fox. There we go. Now let's try it again. Boop. It's going to take a second. This is what's different. What changed?
We're only seeing part of the curve now.
Yeah. Whereas before we were seeing what looked to be kind of a loopy curve. Now we're only seeing a chunk of the curve, a chunk of the curve, a chunk of this curve, and a tinier, even still, chunk of this curve. How does that make sense? There's no time axis on this graph. So how did that change what got produced?
Is it
Anybody
kind
want
of
to take a
like
step?
in parametric equation stuff, like where you had to make your like a third window open almost so it can go all the way around so we can find
Yeah.
integral?
So what you're actually seeing is the time determines how much of the curve to draw. Literally, how long do you run along this path before you stop? And so from 0 to 1 is this much of each one of these curves. If I change this to 0 to 2, it's this much. Notice each one of those curves is much longer, right? How much longer? Well, 1 unit of time longer. And if I go 0 to 3, no big surprise, it's going to be even more still. Now, if I remember correctly, oh, I can't remember. Does anybody remember what the code is for making the curves thicker? Is it thickness?
Pretty sure it's thickness.
Is it thickness? Well, let's see if I can get down with the thickness.
Oh, it's
No.
spelled wrong. There's an extra E in there.
Thickness. Yeah, that's thickness. I don't know if I try thickness equals 3. Is that going to do it? Let's try something bigger. Let's do like 6. Oh, look at that. Much better. Easier to see. Take a look at that. The red curve is almost gone around, whereas this turquoise curve looks like it's maybe about halfway. So what does that tell us about these solution curves on this phase plane? They're all, they look to be all kind of loopy, but they don't all move at the same rate. In other words, the curves that are closer to this center point seem to be moving faster, right? They're covering more ground. And if I go 0 to 4, that red curve is almost done. It's almost completed a loop, as opposed to this guy out here who's is just rounding second base at this point. But watch what happens if I jump back out to 10. Oh, shoot, I changed the wrong thing. Darn, not f equals 10, t equals 10. You see how those curves all of a sudden they went from being smooth to being kind of herky-jerky, and it looks like they're kind of herky-jerky, like on top of itself. What you're actually seeing is a series of herky-jerky line segment curves that have looped around. Remember, the red one looped around and it was almost a little over 4 by the time it made its first loop. This is 10, so it's probably gone around twice, maybe even more. But that turquoise curve hasn't quite made it around twice. And so you can see the herky-jerkiness we're basically letting time roll by, and Maple's doing its best to approximate the curve. But obviously, it's not doing a very good job with the step size on this, right? See this right here? That's just a big step. And so Maple, there's two ways that you can deal with this. There's the num steps, and then there's also the other one is step size. So I'm going to try step size of 0.1 just to see what happens. And Maple created a little bit better. It's still a little herky-jerky out here, but a little bit better. If I try 0.01, much smaller step size, I'm producing a graph. Takes a little bit longer, but it produces much smoother curves.
So if we let time go to infinity, would our population just kind of be doing like this weird little higgly jiggly thing forever?
Yeah. So watch what happens. As a matter of fact, and this is nice if you have Maple up and you want to try typing this in. That's great. But let me show you what happens. I remove the step size thing, and if I change this to from 0 to 100, watch what happens. It's basically trying to do the same number of steps, but now each one of those steps is enormously big. And so these are terrible approximations of what the solution curves actually look like. Because Maple's not dumb. It's like, dude, I'm not going to do all these computations unless I really have to. And so it figures this is probably good enough. This step size is, or this number of steps is probably good enough. But when you start asking for a really long period of time, you need to make up with that by making it a really relatively small step size. So from, go ahead.
There's no like balance of population with this, right? Like with the squirrel, we found where he would get 40 nuts forever. But
so the question comes up. What happens if we start off at an initial condition of 0 to 2? So the red, it would be the blue curve. Does the blue curve ever reach equilibrium?
No.
Yeah, based on what we're seeing, it just kind of goes around and around and around. Not a circle per se, but it's following this weird shaped guitar pick of a path, right? And you're like, that's a weird shape, but it never approaches equilibrium. Can you see where the equilibrium is on our graph?
It's a weird little spot in the middle where there's no,
Doop.
yeah.
It's a little bit more than 1 on the rabbit population, 10/9, and about 1 2/3 in the fox population. As a matter of fact, if I add one more initial condition, and I make this one 0, comma, what was the rabbit equilibrium value? I think it was 10/9, wasn't it? You guys have your notes.
Yes.
10/9. So if I do 0, comma, 10/9, comma, 5/3, and let's make this one, because I got to give it a color. So let's make this one black so it really stands out. And I hit enter. Where the hell is it? Where's the solution curve associated with that initial condition?
It's just that one point in the middle, right? There's no curve if there's no movement.
There's no curve if there's no movement, and there's no movement at an equilibrium solution. So it doesn't show up. It literally doesn't exist as a curve on the RF plane. So if you want to see it, there's two things that you can do if you really want to see this. One is we're going to change these change this initial condition just slightly. I'm going to make this go from 10/9 to 10.5/9 and make this go from 5/3 to 5.5/3. I'm cheating a little bit. I'm making the R and the F values slightly bigger than they need to be. And what we see when we do this is a circle. And that circle is going right around my equilibrium. And I can make it smaller now. I can go, 10.1 and 5.1. And sure enough, it starts looking more and more like a point instead of a path. But it's still a circular path, right? It's still a a curve, right? A solution curve. But if I make it 10/9 and 5/3, it doesn't show up because there's no motion. That means that there's no curve that we're drawing.
Would there ever be any like situations where we kind of have something fall into an equilibrium?
Absolutely. In this particular example, the answer is no. It looks like if you are not on the equilibrium, you never get to it. You never even approach it. The only situation that we could have added and we didn't is if I add one more to account for, remember one of those foxes or rabbit, if you're on the axes, if I add an initial condition for the rabbit population starts off at 1 and the fox population starts off at 0, and then another one for the fox population starts off at 1 and the rabbit population starts off at 0. And I'm going to have to give those colors as well. So let's just do black for both of those because we'll be able to identify those pretty easily. You can see we start at 1, 1, or excuse me, 1, 0, and phew, it takes off, but it only ever goes along the rabbit axis because if there's no foxes, the rabbit population explodes. And if there's no rabbits, the fox population decays straight down towards the origin, just as we predicted it would by examining the equations. Pretty cool, huh? I think it's pretty cool. There's one more cool trick that we have not seen before, and I'm going to show you one more cool trick, and this is a differential equation or a DE plot trick. If you're in DE plot and you really, really, really want to know what happens when you take a look at the time dimension, then we need to add a third dimension. And so we do that by, at the beginning, instead of a DE plot, we say DE plot 3D. That's it. That's the only difference. And what it's going to do is turn this phase plane into a three-dimensional graph. Now, this is the one that I'm most worried about my computer being able to produce and manipulate. But let me try it. Let me see what happens here. Not only does it produce a three-dimensional graph, but this is a manipulable three-dimensional graph. Those of you who have used Maple for other classes, you'll probably recognize the three-dimensional picture. Now notice, that looks exactly like what we just saw on our DE plot. The only thing missing are the little red arrows, right? But what you're seeing here is looking straight down the time axis. This is the f-axis right here. This is the r-axis right here. And we are staring straight down the time axis. And that's what it looks like. This is what the phase plane is. It is literally the compression of that three-dimensional curve onto a two-dimensional space. Just like earlier I said, the phase line is taking a plane and smushing it down to a single line. The phase plane is taking three-dimensional space and smushing it down onto a two-dimensional surface. The fancy word in mathematics for this is projection, right? This is a projection of three space onto a two space manifold. Now, the cool thing is that I can turn this and see pretty easily, oh, each one of those solution curves on the phase plane is actually kind of a curlicue in three space. And what they're doing is moving around the equilibrium value, right? So if you start off on that blue curve or the red curve, to our untrained eye looking at the phase plane, it looks like we're going round the outside, round the outside, round the outside of the equilibrium solution. But in actuality, what we're doing is we're going on a helical path around the equilibrium solution. And the equilibrium solution, remember that black line in the middle? Well, it's not really a line, it's just a really slightly wiggly curve. What would it do if I change this to the actual equilibrium value of 10/9 and 5/3? What do you predict we'll see in three space?
Just a straight line.
Sure enough, in three space, that equilibrium solution that disappears when we're staring at it straight on down the t-axis, all of a sudden, all you have to do is just shift it just a little bit, and you're like, oh, there it is. That's the solution curve. The equilibrium solution literally means no motion in the r or the f dimensions. The only motion that the equilibrium solution goes under or goes through is motion through time. And for those of you who are getting into some physics, congratulations, this is at the heart of relativity. The idea that we are all moving right now, sitting in our chairs. We're just moving through time instead of space and time, right? We're moving through this extra dimension that when you're looking down the barrel of the t-axis like this, you can't see it because the t-axis is invisible when you're on the phase plane. But the phase plane you can think of as riding up through time. And the curve that appears because we're riding up through time on that. So we've
Could you go
gone.
back up to the code that you made?
Sure, absolutely.
I'm going to snatch a screenshot of that if you don't mind.
Absolutely. I'm also going to post this Google or this Maple file will be available after class as well. And I want you to play around with it, use it. So I've kind of condensed a lot of several examples all into one because I wanted you to see sort of the evolution of first we started with a DE plot and then we added some initial conditions and now we have the ability to see it three-dimensionally. There's one more trick that we can do with a DE plot. I'm going to take off the 3D bit and we'll go back to the normal, boring, plain old two-dimensional DE plot. There's one more piece of code that we can add at the very end. And the piece of code that we can add is just one more option that you can throw on the end. And it's called the scene option. And so what I'm going to do is scene equals, and then in brackets, I have to name two variables that I'm interested in. And specifically, I'm interested in the t variable and the r variable. Now, what this is going to do is it's going to produce all these solution curves for all those initial conditions, but it's going to ignore the f variable. It's going to produce the solution curves only in terms of r and t. So what we're going to see when we hit enter is a series of t along the horizontal axis and r along the vertical axis. And so pretty quickly, you can identify and go, hey, yeah, remember that curve when it just kind of takes off and grows exponentially? That black curve right there, that's the initial condition where there's no foxes. And the rabbit population just grows and takes off forever. And this one right here, that kind of goes straight across and doesn't go up and doesn't go down, the rabbit population is in equilibrium. And that's the one where there's a specific rabbit population and a specific fox population, right? That's the 10/9 for rabbits and 5/3 for foxes. And then this one down here, this black one down here, that's where there's no rabbits to begin with. And if you don't have any rabbits to begin with, there's no change. But all the other ones are doing really interesting things. Look at this turquoise one. It kind of dips down, gets really close to zero, but then zoop, shoots back up and then drops back down and then zoop. And if we were to extend the time out on this, you would see that it's very cyclical. It's cyclical on this graph because what's it doing on the phase plane? It's going around and around. And when you cut out one of your variables, if you draw a circle and then you take your graph and you look at it in terms of only one variable, you don't see a circle anymore. You see a back and forth and back and forth and back and forth and back and forth. You see a periodic function. When you take that graph that was kind of a weird shape like this and you pay attention only to the rabbit population, you're going to see it go back and forth. You're going to see the rabbit population drop and then increase and then decrease and then increase. And so all those other curves are showing you the periodic nature of the rabbit population. And it, by the way, in case you're wondering, we could do the same thing for fox population. And get a good look at that graph, because the fox population is going to be a little similar, but not exactly the same. Because if they were exactly the same, then we'd have a very symmetric graph. And so notice we have the fox population stays constant because it's in equilibrium. The fox population stays constant because it's 0. The fox population drops off to 0, towards 0, because we started off with no rabbits. But all the bright colors, those curves are fox population increases, and then it decreases, and then it increases, and then it decreases. And as the rabbit population goes up, that means the foxes have more prey, and so they increase, and then the rabbit population goes down, and so there's a bit of a delay, and the fox population starts to decline because the rabbit population is declining. And as we lose foxes, then all of a sudden the rabbits are like, hey, there's not as many predators, and they start to grow again, and the cycle begins anew. And you wind up with this really interesting situation where you can have, let me do this here, I'm going to grab this same code. I'm just going to reproduce that code right below, but I'm going to do it for the rabbit population. And so if I do this right, I can fit these two on screen. Let me try to decrease the zoom factor on this. So maybe the graphs are still really big. But notice how they have the same t-axis, the same scale. And so we can see that at about 5, it looks like the green curve, that bright green curve, is at a maximum for the rabbits. At 5 for the foxes, that bright green curve is kind of in the middle, but it's on its way up because there's lots of rabbits, and so the fox population is growing. You can, if you want, grab onto a particular solution curve and drag it into the other graph and do this. I don't know if you've seen that before on Maple, but you can actually grab graphs, one curve from one graph, and then drop it into another graph. And so that bright green one, if I kind of get rid of all these others, the bright green here, that's the rabbit curve. The bright green here, that's the fox curve. And so I can actually see what's going on with both of those. So there's a lot, I know there's a lot to process here, but I wanted you to see kind of all the cool stuff that we can do in Maple. We can do a DE plot to see what these solution curves look like, even if making sense of what the actual equation for the solution is really complicated. We can still make predictions using the graph, using the DE plot. And we can actually create a 3D plot to see what's happening over time. And on top of it, we can also use this scene command to say, I just want to focus on what's happening to the foxes. But I can't ignore the dr/dt equation because they come as a pair, right? They come as a one whole unit. The system has to be solved together. I can't solve them separately. It doesn't make much sense. So I can use this scene command to take a look at what's happening to one population and ignore the other one temporarily. So there's a lot of stuff that we're doing here. So you might be wondering, yeah, this is great, Steve, but what I really wonder is it possible that if I were to get rid of, let me get rid of the scene command here, and we'll just look at a straight up differential equation system like this. Stephen actually asked a really good question. Does that mean that nothing heads towards equilibrium? And the answer is, yeah, because the rabbits and the foxes are always trying to find that perfect balance, but they never get there. So what can we do to make this a little bit more realistic? The foxes depend on the rabbits, and the rabbits just are there for food for the foxes. But we all know rabbits can't grow forever. There's an upper limit. And so let's modify the equation. Let's manipulate our equation and find a way to make sense of a modified system to account for limited growth. So on this page, what I've done is I've taken my rabbit population, the dr/dt, and I've tacked on an additional little bit here. And this additional little bit, right here, this is what allows me to create a limited growth model. And if you remember, that looks very, very similar to the logistic curve that you guys played around with. The logistic model has that 1 minus something where it's R over 2, where that's like the carrying capacity, right? And so this is suggesting the rabbits have a carrying capacity of 2. If they ever got up to 2 units of population, that's the upper limit for rabbits. But of course, the foxes are still there, and they're still going to be eating the rabbits. So don't get too worried. So what does this mean? Well, what does this tell us? So as the rabbit population approaches 2, we see limitation on growth. So the rabbit population doesn't continue growing forever. Even in the absence of foxes, the rabbit population kind of dies off. But if the rabbit population is much, much smaller than 2, growth is essentially exponential. So if R gets really, really close to 2, it starts to slow down. The growth part of that equation becomes closer to 0, as we've seen before. What happens if R is bigger than 2? What would we expect if the rabbit population magically, like I dumped a whole bunch of rabbits in a place where their carrying capacity is much, much lower? What would happen if I had a rabbit population bigger than 2? What does my equation predict would happen?
They would die off a bit.
Yeah, 1 minus, well, R over 2, if R is bigger than 2, this is 1 minus something bigger than 1. So it would mean not growth. That term is no longer growth. That term is decay. So if R is greater than 2, we expect rabbit population to R of t to decay. At least until they get down to that limitation level, that value. So what we see happening, or what we expect happening, is that R and F, let me kind of write down underneath here, R of t and F of t solutions to this system behave differently. Than before. But how differently? Well, let's find out. Let's hop back over to Maple and ask Maple, hey, can you really quick figure out what's going on with this system? Can you make a prediction for what to expect? And Maple says obligingly, absolutely I can. And so I'm going to change my share here to the Maple screen, a new Maple screen. And let me bump up the size of this thing. So we're going to modify our rabbit differential equation. We'll call this RAB2. And so before we had something that looked like this. But with RAB2, where we have a whole brand new situation where there's limited growth, we get a DE plot that looks like this now. Now notice the difference. With an initial condition, the exact same initial condition, well, not the exact same, I think this one is a little slightly different, but with very similar initial conditions. This is supposed to be 2. Boop, 2. Hold on, there we go. With the exact same initial conditions, you can see we're talking about 2 very different situations. Notice the situation where we start off with all foxes and no rabbits, that doesn't change. It's still decay straight down the f-axis. Decay straight down the f-axis because we didn't modify the fox population equation. But if you start with all rabbits and no foxes, before it was growth. Now it's decay down to this new equilibrium position. And more interestingly, if you start off at 2, 2, which is like this point right there, and you play the clock forward in the old system where there wasn't limited growth, the rabbit population, we're moving in this direction, the rabbit population dies off as the fox population grows, and then the fox population dies off, which encourages the rabbit population to grow, and then the fox population grows, and we're in this cyclic nature. But now, with the modified equilibrium, or the modified for limited growth, we have the rabbit population dies off, and then the fox population starts to die off, then the rabbit population grows, and then it looks like it's headed straight for that equilibrium. And that equilibrium point is not in the same place as it was up here. It's in a different place. But it's an equilibrium point that apparently everything is going to head towards. And we can test it. We can try another initial condition. So something that's on this screen that we're going to be able to follow, something like, I don't know, 0, 4, 1. And let's make that one, I don't know. We've done green, blue, purple. Let's make that one red. Take a look. We start way over here. Very different initial condition. But what's the end result for our rabbit and fox populations? If we play the clock forward, whether we started here or we started here, where do we end up? And that wasn't a rhetorical question. I'm really wondering, where does it look like we end up? We wind up at the equilibrium, this new equilibrium point. And if you were to imagine zooming in on the graph, you'd see both of these curves get really, really close together, but they never overlap. Because if one solution curve crosses another, that breaks the rules, right? That can't happen. These are autonomous differential equations. Their solutions don't lap over on top of each other. They may look like it on the graph, but that's not really what they're doing. And so if you were to zoom in closer and closer, these two curves are getting closer and closer and closer. And if you were to play the clock forward more slowly, like for example, we're going from 0 to 20. What if I go from 0 to 10? You see the same solution curves. If I go from 0 to 5, you see the same solution curves, but they don't quite get as far. These two curves are still headed in the same direction, but they're not quite there. We have to play the clock far enough forward in order to see those two curves, which means that the last 15 seconds worth of time units worth takes a tiny little space here, which tells me that there must be really a small amount of motion of the actual solution curves as they're moving around. So there's very little motion here. The first couple of units of time apparently move very far and very fast. But the last couple of units of time on these solution curves are not moving fast at all. And so we can take a look at this in three-dimensional space. And we see the solution curves as they appear on the phase plane are actually just, well, this one seems to be like corkscrewing, but then kind of flattening out to what appears to be a straight line in the time dimension only. And that curve that looks like it just drops from 3 to 2 is actually exponential decay if you consider the RT plane. That's what the RT plane looks like. This is the scene graph, albeit vertically this way. It's the scene graph for R, T, R. Right? So we can make estimations, we can make guesses as to what's going on, and we can manipulate the system in a bunch of different ways. I'm going to switch back over to the document camera so that we can add some notes to our document here. So R&T solutions are different than they were before. That is to say, they're headed towards equilibrium. And not just the ones that are on the axes, not just the ones that are headed towards the origin or headed away from the origin. Any solution curve is now headed towards equilibrium. Either the origin, where if there's no foxes, it would head towards a rabbit population of 2, or if there's foxes and rabbits, they all head towards that new special equilibrium. So I'm going to draw a couple of graphs that we could produce in Maple by doing a scene. The first one will just be rabbit population versus time. And if we started at a rabbit population of, say, 2 over time, then, and this is with a fox population, right? So this would be, we'd see an initial dip, and then it kind of goes up, and then it kind of levels off like this. And the reason for that is because at the same time, we have a fox population graph that if the fox population starts at 2 as well, or thereabouts, initially the rabbit population being high is good for the foxes. And so they grow initially, and then the rabbit population is decreasing over time, and so the fox population starts to drop. And it craters out, and then it kind of comes back up and hugs a horizontal. And so what you're seeing is you can have the same t-axis, the same scale on the t-axis tells 2 different stories, whether you're talking about the rabbit population or the fox population. And in order to get these, just as a note, we use the scene option with a DE plot in Maple. So this guy right here, this would be scene equals t comma r, and this one over here would be scene equals t comma f. Oops, I forgot my close brackets there. So we can make those graphs for the initial condition of 2, 2, and verify that that's indeed what it looks like. So both of these graphs are telling a slightly different story only because we're focused on a slightly different population. So I'm just going to make a little note and say both graphs show what happens after our initial condition equals 0, 2, 2, right? And let me move that out of the way. Forgot about that. Equals my initial time, my initial rabbit population, and my initial fox population. So both of those graphs are telling us what's going on. The cool thing is that we don't have to see them separate from each other. On the phase plane, we're taking both of them together. We're treating them as though they're parameterized equations, parameterized with respect to t, and we're looking at both of them on the same plane. And so the only other thing I'm going to draw on this page down below is what happens when we put them together on the RF plane. So both of these come together and they produce a graph that looks something like this. If you start at 2, 2, there's your initial condition. You know that initially, and I'm just going to kind of scoot it up so you can see, initially the rabbit population decreases while the fox population increases. So rabbit population decreases means that way, fox population increases means that way. So we're going to wind up with a curve that's going to go like this. And it's going to cycle in and kind of head towards some equilibrium solution. And I'm just drawing little arrows to kind of show the direction that that curve is going. And so this is our phase plane. So this phase plane curve shows both populations changing together. But the kicker is it hides that time dimension. Right? We can't see the time dimension because it's coming straight out of the paper. So there's a lot for us to kind of process in terms of the information. So, and I know, I completely understand that this is a lot to really kind of wrap your heads around. But we've got equilibrium solutions that mean actual locations on a plane, not lines anymore, but actual points on the plane. And we can find them doing the same thing that we did before by setting the derivatives equal to 0. But we now have to make some sense of what's going on with that. So what I want to do right now is give you a chance to breathe a little bit and pay attention to and take a look at what's going on the 2.1 classwork. So if you kind of flip over to the 2.1 classwork, you'll see that I've given you a task. This is all about an organism, or two organisms, a predator and a prey. But it's a completely different situation. It's not rabbits and foxes. This time, it's elephants and mosquitoes. And you don't think about elephants being the prey, but they are. They're consumed by mosquitoes, right? So it's kind of a weird situation. But what I want to do is turn you guys into, or put you guys in your groups and have you look at just question number 1. And question number 1 has got like 6 parts, but I really want you to take a look at the equations and see if you can answer those questions. Now, nothing in there is asking you to hop on Maple and make the graphs that we were making. You can definitely do that if you want, but that's going to take more time away from you actually talking through the solutions. So I'm going to hit pause on, I'm going to stop sharing actually, but I'm going to hit pause on the recording and then have you guys take a look at the 2.1 classwork, just question number 1 with your groups. Does that make sense? So we're going to do this for like maybe 10 minutes. Give you a chance to stretch your legs, move around a little bit, talk to each other. Yeah, stretch. There's a lot going on. So I'm going to hit stop on the recording here.